Hello everyone, welcome back to my channel. It's Alice here from Thriving Academy. In today's video, I'm going to talk about monosaccharides. Basically, I'm going to show you a definition of those compounds, their classification, and stereoisomerism. So please, if you are new to this channel, please make sure you subscribe and hit that notification bell so that you won't miss any of my new uploads. And if you found this video helpful, please share it with others so that they can enjoy too. So let's go and get started. So monosaccharides are basically the simplest form of carbohydrates, and they are the basic unit of carbohydrate. So what do we mean by this statement? For example, if this is a home, a house that is built by bricks and all those things, right? So if this home is a carbohydrate, for example, so those individual blocks that are joined together to form this building are the monosaccharides. So monosaccharides are just small units that they are joined together to form carbohydrates. So monosaccharides are majorly classified based on two major classification. The first classification is based on the functional group of the monosaccharide. Okay, and from basic chemistry we know when we say functional group, we are referring to a group of atoms that determine the physical and chemical property of a compound. Okay, so that's that. So based on this classification of functional group, monosaccharides have two subgroups. The first one are called aldoses. And what do we mean by these aldoses? When we say aldoses, those are monosaccharides that have an aldehyde functional group. Aldehyde functional group. So how does this aldehyde functional group actually look like? This is how an aldehyde functional group look like. So basically, all monosaccharides that have this functional group are called aldose monosaccharides. We're going to see those of them later in this video. So the second main subgroup based on this functional group classification are ketoses, and those are monosaccharides that have a ketone functional group. A ketone functional group. So how does ketone functional group actually look like? This is how a ketone functional group look like. Where this R can be carbon chain, any number of carbon, and this R prime 2 can be any number of carbon. So all monosaccharides that have this kind of arrangement in their structure are grouped into ketoses. We're going to see many of them in this video. So that's that for the classification based on functional group, and let's head into the second classification system. The second classification is based on carbon length. And what do we mean by this statement? When we say carbon length, we are referring to the number of carbon atom in that monosaccharide, for example, right? So this is what we mean, the number of carbon atoms. So this is based on how many carbon atoms are in that monosaccharide in question. And based on this classification, we have subgroups of one. The first one in this is called stereoisomes. Are called what? Stereoisomes. So what does this actually mean? If you look at this word, you see tri here, right? And basically tri means what? Tri means three, right? So these are stereoisomes. These are monosaccharides that have three carbon atoms. So you ask me now, hey Salis, what's happened? What about 1 and 2? Basically, there is no non-carbohydrate with 1 or 2 carbons. So the first carbohydrate, the first monosaccharides started from 3. Those are the stereoisomes. So let's see their structure. Example of stereoisomes are number 1, this compound you are seeing, and this compound is called glyceraldehyde. Glyceraldehyde. Okay, so there's something really interesting. Let's take a look at this structure. You see, this one have 1 carbon, second carbon, third carbon, right? That means it have only 3 carbons. Okay, but there is something really interesting that I want you guys to see here. Look at this structure. Look at this arrangement here. CHO, right? The CHO, it looks like something like this. It's looking of this nature. Okay. Remember, I show you that this can be carbon, right? So you see here is a carbon. Okay. So if we have this group, what does this group mean? This group is an aldehyde group, right? It's an aldehyde, right? And we have an aldehyde functional group in a monosaccharide. We'll call that monosaccharide an aldose sugar. Okay, an aldose monosaccharide. So basically, glyceraldehyde is an aldose monosaccharide that have only 3 carbons. So this second example you are seeing is called dihydroxyacetone. Okay, and it also have 3 carbon, 1, 2, 3. But there is something really interesting. Look at this structure. What does this look like? It look like something like this. Okay, something like this. Yeah, I told you this can be carbon, this can be carbon too. See, I have carbon here, I have carbon here, right? And what do we call this thing? We call this structure as a ketone functional group. Okay, ketone functional group. And when we have an aldehyde that have a ketone functional group, we call that aldehyde as a ketose. Cool? As a ketose monosaccharide. So dihydroxyacetone is a ketose monosaccharide that have only 3 carbon. Right? So let's be looking at these structures. Let's be looking at this. So the next category in this classification are called tetroses, right? And this word tetra is from tetra, right? And tetra means 4. So tetroses are monosaccharides that have only 3 carbon atom. They have only 4 carbon atom. Okay, so example of those are erythrose. Yeah, this is erythrose. And see, we have 1, 2, 3, and 4 over here, right? And if you look at the structure, this is looking like an aldehyde, so this one is a ketone. Another example is erythrulose. This compound as seen down here is called erythrulose, and if you see, it have 4 carbon, and also you have a ketone function group, meaning it is a ketose. Okay, so let's move further. So the next category here are called the pentoses, right? And if you can look at this word, it derived from penta, right? And penta means 5. So pentoses are monosaccharides that have 5 carbon atoms. So let's see. 1, 2, 3, 4, and 5 over here, right? And this is called ribose. And if you can look at this, you see that they have an aldehyde functional group. So ribose is an aldose monosaccharide that have 5 carbon sugar. Another 5 carbon atom. Another example is ribulose. And this one also have 5 carbon. You can see 2, 3, 4, 5, right? But it have one. There is something really interesting, right? It have this ketone functional group. Okay, so the next group here in this classification are called hexoses. And look at this one, it derived from hexa, right? And hexoses, so in this regard, hexoses are monosaccharides that have 6 carbon atom, right? And you can see from here, right? 1, 2, 3, 4, 5, 6, right? And this one is called glucose. This compound is called glucose, and we know this is the main source of energy for main source of energy that is found in carbohydrates. So hexoses are the most important monosaccharides. They are the most utilized. They are the most found in dietary foods that provide energy. Okay, so another example that I have here is fructose. So this compound you are seeing down here is called fructose, and it have also 6 carbon, right? Yeah, 6 carbon as well. But fructose is ketose, right? The functional group is a ketone, so it's a ketose. So there are other classification. There are other subgroup which are called heptoses that have 7 carbon atoms, but they are less rarely found, and we are not going to cover them in this video. So now let's look at the stereoisomerism in monosaccharide. This is the most very important feature of monosaccharide, and let's see what stereoisomerism means. When we say stereoisomerism, we are referring to phenomenon in which compounds have the same structural formula, but they differs in their spatial arrangement of atoms or groups. So the compounds basically have same kind of atoms, same kind of groups, but the only difference in the arrangement and the position. That's basically what we mean by stereoisomerism. So let's take a look into these 3 compounds. Basically, I don't know any compounds that have this structure, but I'm just using them to explain myself. So if you look at the compound number A, you see that it have PQRS group. Compound B have PQRS group. Yeah, almost the same PQRS, right? And compound C have PQR. And no S group, but we have 2 R's. Okay, so let's see. Compound number A have P at this position, but in this position is an R, right? And what does this mean? This means that these 2 compounds are stereoisomers because they have the same groups, but there is only the only difference is in the spatial arrangement of the groups. So in this compound, P is to the right, but in this compound, P is to the left. In this compound, in A compound, R is to the left, and in this compound, R is to the right. So that is basically what we mean by stereoisomers. Stereoisomers, compounds that have same group but they have different arrangement. Okay, so this phenomena of stereoisomerism only happens in compounds that have a carbon called chiral carbon. Chiral carbon. And what do we mean by chiral carbon? Chiral carbon is a carbon that have 4 different groups. So let's see. This one have Q is different, R is different, S is different, and P is different, right? Then P is different, S is different, R is different, and Q is different, right? So that means these 2 compounds can exhibit this phenomenon. So let's see the compound number C. Compound number C have Q, R, P. So the other 2 groups are identical, and this means this compound is not a chiral carbon. And in this regard, it cannot undergo stereoisomerism. Yeah, stereoisomerism is prohibited. It's not happening in this kind of carbons, right? So let's see features of this chiral carbon. Chiral carbon, as we know, have 4 different groups. They are attached to 4 different groups, and they are optically active. What do we mean by optically active? Optically active in the sense that this compound, this chiral carbon, they rotate plane polarized light. They rotate plane polarized light to 2 different direction, 2 opposite direction. So if this is a plane polarized light, right? So this chiral carbon can rotate the plane polarized light to 2 opposite directions. They can rotate it to this direction, and it can rotate the plane polarized light to this direction as well. So for this reason, stereoisomers exist in two forms. The first one are called dextrorotatory. Dextrorotatory, and they are shortened as D. And these dextrorotatory are stereoisomers that rotate the plane polarized light to the right. Okay, so if this is a plane polarized light, the dextrorotatory forms of stereoisomers, they rotate it to this direction, that is to the right direction. The second group are called levorotatory, or also shortened as N, stereoisomers, right? And these are stereoisomers that rotate the plane polarized light to the left. Okay, so this is basically what uh, stereoisomerism is. So we have two stereoisomers, either D or L stereoisomers. So let's see how can we find out how can we know if a sugar is D, that means it rotates the plane polarized light to the right, or is L, meaning that it rotates the plane polarized light to the left. So we can know whether a sugar is D or L by the orientation of our hydroxyl group and our hydrogen group in the penultimate carbon. And what do we mean by penultimate carbon? When we say penultimate carbon, we mean second to the last carbon. Second to the last carbon in the monosaccharide. So when the OH group, that is the hydroxyl group, is to the right, that sugar is a D sugar. Okay, so you have to get this. If you have OH group to the right in the penultimate carbon, that sugar is a D sugar. And if we have our hydroxyl group to the left, that sugar is an L sugar, meaning it rotates the plane polarized light to the left. So let's have example of see from some of the monosaccharides that we use in previous example. So now my penultimate carbon is this carbon, right? And where is the orientation of the OH? This OH is found at the right, right? And meaning that this is a D monosaccharide. This monosaccharide take the plane polarized light to the right. So let's take a look at this compound. This compound is glyceraldehyde group, that aldose triose sugar, right? So this is my penultimate carbon, that is the second to last carbon, right? This is the last carbon, right? And the position of this OH, that is the hydroxyl group, is to the right too, right? And that means this also is a D. Then I should call it as D glyceraldehyde. D glyceraldehyde. Okay, so let's take a look at this one too. This is called erythrolose, right? If you remember, this is erythrolose, right? And have how many? And it have 4 carbons, right? Yeah, this is erythrolose. So now my penultimate carbon, this is the last carbon. So the last carbon will be this one, right? And the orientation of my hydroxyl group is to the right. And what does this mean? This sugar is also D. So for this reason, in conclusion, most of the naturally occurring monosaccharides and carbohydrates in general are D sugars. So the orientation of their OH group in the second to the last, in the penultimate carbon, is to the right, meaning that they rotate the plane polarized light to the right. So this is all we can cover to you on the stereoisomerism. So please, if you found this video helpful, make sure you share it with others, and if you found it really nice, please give it a thumbs up so that YouTube can recommend it to other viewers as well. Thanks for being with me all the way to the end, and I look forward to seeing you next time in my next video. Salis Idris, Thriving Academy.